Hi, my name is Lucas Aran, and today, together with Gabriel Rebelo, I'm going to present to you the DFedForest system, Decentralized Federated Forest. Also, Gustavo Franco Camilo and Lucas Chagas Brito Guimarães are co-authors of this paper, under the orientation of Professor Otto Carlos Muniz Bandeira Duarte. We all are from the same research group, the GTA, Group of Teleinformatics and Automation, from the Federal University of Rio de Janeiro. So in traditional machine learning, what we have to do is to take a data set and split in two different parts. The first one is the training data set, and the second one is the test data set. The training data set is used to fit a model or to train a machine learning model. And the test data set is used to evaluate the model that we create in the last step. However, this is done in a centralized approach, that we have all the data on the same location to train and fit our models. However, this approach is recently put in danger because security issues and privacy issues of the data restricts the centralized process. So we have to choose another way to process this data to create our models. So one way to produce this data to fit our models is to apply some techniques to preserve the privacy of this data. And the first one is the de-identification. So we take the data set and remove some features that reveal information from the point of the data was collected. The second one is the differential privacy. It is basically adds noise to the data set to not reveal specific informations. And the third one is the homomorphic encryption. Basically, what you do is to take a data and encrypt, but when you share this data, the person that receives this data can apply some arithmetic functions like sum or product, and not revealing the data encrypted. But we have a scenario of too many devices and big data, so we have too much information on the network, and we want to reduce this information. So we have to think in another approach that keep the data privacy and update models and train a better model. So in 2016, the Google presents the Federated learning. That is basically an approach to train a model that uses data from many devices, but the data remains on the devices. They do not share any data. They only train a model with the local data, but the data remains on the devices. So basically, the training can be divided by two agents. The first one is the client that uses the local data to update the model and share the response, the results, with the server. And the server is responsible to take the response of the client and aggregate in a big and better model. But this approach has a problem because it assumes that the client updates correctly the model, and also the server will behave according to the protocol. But in a real scenario, you can have a server that's managed by some malicious agents and try to harm the clients, and also you can have a client that's trying to harm the global model. And also this approach have a single point of failure because the server stores the model. So our proposal on this paper was to use a federated learning, but in a decentralized way, without the server to train and store the model. Our proposal to produce this decentralized system is to use blockchains, because the blockchain acts as a ledger that is immutable and records every single model shared on the network and who shared this model. And it is impossible to deny that you share some model because you signed the model before you share. So if a domain starts to behave maliciously, you can easily verify that it is a malicious domain and you can punish them. And since all the domains have access to the blockchain, they can verify the blockchain for new models and download them to update the local forest, and in this way improves the performance of classification. Here we have an example that the DFedForest with 4 domains. Here we have the domain 1 and domain 2 sharing the local decision tree on the blockchain as a reference. So the domain 3 can consult the blockchain and finds the model of domain 1 and domain 2 to aggregate to the local forest. So to create a prototype and evaluate our proposal, we choose the Hyperledger Fabric as the blockchain because it is a permissioned blockchain and we want to control what domains made part of our network and eventually exclude some domains that behave maliciously. And to create the decision tree models, we use the scikit-learn. And to evaluate and train our models, we use the dataset CTU13, that is a network dataset that contains benign and malicious samples of flows. So we base our system on the random forest. Basically, the random forest have an easy interpretation because it is made by trees, and trees have an easy interpretation of the results. And also, the random forest offers the advantage of reduced overfitting, because when you use just one tree, it can easily overfitting on the data that you're training. But when you use several trees, it is hard to overfit all the decision trees that you use on the random forest. And this algorithm can be implemented in parallel. So the main idea here is to create different decision trees and different domains. And each domain creates its decision trees with the local data and share the model on the network. And basically, the other domains can create a better random forest with information of other domains. So here we have an example of the system execution with 2 different domains. The first domain has access to the network and it captures packets to create a dataset. After this dataset is created, it can use to train a decision tree model, and the results is stored on a storage server. After that, it can issue a publication transactions that contain a reference of the model and get a confirmation when the transaction is added to the blockchain. And now the domain 2 can consult the blockchain for the new model and get the model reference that he wants, and with the reference consults directly the storage server for the new model. And with the model, he can test locally with the data if this model is not a malicious model, and if passed in the test, it can increase the local forest with models of the domain 1. So now Mr. Rebelo will introduce our threat model and make a complexity analysis of our proposed system.
Because our system is built to work in a trustless distributed environment, of course we expect attacks to happen. And in our attacker model, we expect 4 types of malicious actions. The first one is sharing incorrect models to attack other domains. Because this is a distributed environment in which participants do not trust each other, we expect attackers to try to publish incorrect or bad models in general, so that other domains download them and reduce their own performance. And to prevent this, we oblige domains to test models before incorporating them. So whenever a specific domain downloads a tree model, it tests that tree model against its own data, and if it's below some performance threshold, it discards that model. And in the end, the domain only gets the good models to create its own forest. The second kind of attack is an attacker can attempt to extract information about other domains' forests. So in this case, an attacker wants to extract information about the forest and predict how that specific domain will classify some sample. And we prevent that by obliging that each domain privately decides which models to use. So whenever a domain downloads a specific tree and incorporates to that forest, we do not publish that in the blockchain. We do not make that public. And thus it becomes impossible for an attacker to know how a specific forest of a specific domain is built, which models that domain uses. The third kind of attack, the attacker can attempt to extract information about other domains' users. So by looking at the published model, it can try to infer which data was used to build that model. And we mitigate that by de-identifying the models. So if there is a specific feature which has a name or a tag, we substitute that by a number. So whenever an attacker looks at the model, it only sees numbers and it can extract no useful information. The fourth kind of attack is an attacker can try to flood the system with empty transactions. Because the models are published in a blockchain and they have to go through a consensus round, an attacker can issue many transactions to stop the system and to stop the useful information from arriving to the domains. And to mitigate that, we identify all the participants in the network. So our blockchain is permissioned, and each domain's credential is published in the blockchain. If a specific domain tries to issue many empty transactions, the other domains can just verify the blockchain and ban that specific domain from doing that. We did a complexity analysis of our system to see how it would perform compared with centralized algorithms regarding training time and test time. So for training time, our system comprises 3 phases. The first one, each domain creates decision trees using its local data. And we assume that each domain does that concurrently because they're independent. So the time complexity of that phase would be O of nt log of nt, which is the same as a Carth algorithm for building decision trees. And by the way, nt here is number of training samples and age is number of trees. The second phase is to store models and publish the references into the blockchain. This cannot be done concurrently because the transactions in the blockchain must be ordered. So the time complexity of this phase is O of age, where age is the number of trees. The third and final phase is the domains query the references from the blockchain and download the models from the server. And in this phase, the time complexity is also O of h because I have to download each tree independently. And thus, the overall training time complexity is dominated by the first phase and is O of nt log of nt, which, by the way, is the same as a Carth algorithm despite building the whole forest, because we assume that each domain can build trees concurrently. Regarding test time, after the forest is complete, it behaves like a regular centralized random forest model in each domain. So the test time complexity in our case is the same as a regular random forest, which is O of h and c log of d. Here nc is the number of samples to be classified, age is the number of trees in the forest, and d is the tree depth. And because we expect models to be trained only once and then test and classify new samples all the time, we can safely assume that in sometime in the future, the number of classifications will surpass the number of training samples. And thus, the overall complexity of our system is O of h and c log d, which is bound by the test time complexity. And this overall complexity is the same as a regular random forest, despite being a distributed forest.
So our first experiment to evaluate the DFedForest is to verify how it is behavior when the data is distributed equally among several domains. So here we choose to evaluate the F1 score metric for each classification model. We propose 3 models. The first one is the random forest, the traditional random forest with the data sharing. It is because we centralize all data on the server and train to fit a model, and after that we test with some part of the dataset. Here we have the random forest with no sharing. So we divide the data between the domains, and after that we train a random forest with the local data. No data of the other domains was used. And the third scenario was the DFedForest that used the models created in other domains to create the local forest. And here we have the number of the trees that were created on different domains. For example, here we have 128 different domains, and each one contributes equally with one tree. So in these two scenarios, the algorithm is made with 128, but here in the DFedForest we have 128 domains, and each one contributes with one decision tree. So here we have the results that when you centralize the data and do not preserve the privacy, we have the best performance. But the solution is not a good one because you do not preserve the privacy. So you have to choose one of those. And the other approach is to no share of data and no share of information, and you train just with the local data. So you have the poor performance and the worst case scenario. So the best way to preserve the privacy and is to get good results is the DFedForest. That's in the middle of the classification performance of the two extreme scenarios. So we can conclude that our proposal, the DFedForest system, it preserves the privacy but do not have a great loss on the classification performance. And in the second case, we evaluate when the data is distributed between two domains, but these two domains have different attacks on the data set. So the attacks on the data set 1 is not the same as the data set 2. So for the domain 1, the data set 2 have new threats, and we want to evaluate how the DFedForest can detect new threats. So here we evaluate the accuracy of the classifiers, and we evaluate the number of the trees on the DFedForest system. So here in the solid line, we have the decision trees that were created locally on the domain 1. And the dotted line represents the tree that were created on the domain 2. And basically the domain 1 tried to classify the samples of the datasets of domain 2 that contains new threats. And basically here we start just with the decision trees created on the domain 1. And we have this performance that is not good, and it is decreased when we increase the number of decision trees created on the domain 1. But when you try to get the decision trees of the domain 2, it is increase the performance of classification and continues to increase when you add more trees of the domain 2. So we can conclude with this experiment that the system can improve the detection of new threats. So when you use the DFedForest system, you can detect more threats that you would detect if you use only the local data to train a model and try to classify new samples. And finally, we have the model sharing time. Basically, is the time to share a model on the blockchain, the reference of the model. And here we evaluate how the times variates when you publish a certain number of transactions on the blockchain. And basically it is linear, the relation between the number of models published on the blockchain and the time needed to confirm these transactions. So we have a low complexity on the model sharing, and it is good to a system have a low complexity because it do not affect the domains that want to share the model on the network, and it's very easy to share new models. So to conclude our work, we present a data privacy approach to machine learning. So we train these models and share no information, no sensitive information, just the model, and try to eliminate any information that reveals sensitive data. The second one is the reduce of loss performance, because you can also keep the data privacy by not sharing any sample that you have. You can use just your local data, but it is not a good approach, and our approach is better than that. We also improve the new threat detection, because when you have two different domains communicating with each other, it can prevent some of new attacks that they suffer if they have different attacks distribution. And finally, we have a low complexity system because it has the same complexity of a traditional random forest, because the main complexity of the system is the classification. And when you train your local forest and you finalize your forest, you only classify new samples. You do not retrain on this case. So the complexity, it will be the same of a random forest, and it is applied to real-time classification because you do not have any overhead on the computation. You have just the same complexity of a random forest. Thank you, everyone.